Greetings, all of you, and thank you for joining this session. As you are aware, this is the first session of several sessions, namely 8 sessions, that are being conducted to assist senior Olympiad enthusiasts to tackle Olympiad competitions, specifically the second round and above. So this is the first session, and let me share with you what the other topics are. So this program is being run by the South African Maths Foundation. I'm sorry about that delay. The topics that will be discussed in these 8 sessions are shown on the screen. This very first one is called Basic Algebra, and I will be the facilitator for that. And the facilitators for the other sessions and their titles are below that. In the entire program, we will be using material from one particular book, which is called 1000 Mathematics Olympiad Problems. And I understand that all of you will have a free copy of that. So it's very important to have this book in your possession so you could make reference to the problems that we will be considering from that book. Right, so to give an example, the very first problem that we will be doing, okay, even before that, you will see here on this top right-hand corner, let me just take this out. You will see a little box there, and this box was obtained by my trying to find out where the problem whose number is 676 appears in the book. So the way to do that is to press Control F, Control plus F, that is the find instruction. And when you do that, this little box appears with a blank space here. And then what we do is type in problem 676, but we must make sure that we put a P in front, and that will take you straight to the problems 676. And when we are at that problem, so this is what happened here when I did that. This problem came up, of course, in the book, and there were many other problems on that same page, but I cut it out and pasted it here. And when then you have the question here, and what you have to do is to try to answer the question as best as you can. And if you, at the end of it, or even in the middle of it, if you want to look for the solution, what you do is you go to that box there which says P676 and click or double click, and that will take you straight to S676. And that is the solution to that problem. It is elsewhere in the book. The book itself is quite a large book. It's got almost 640 pages, and the 1000 problems occur somewhere in the front, and then the solutions occur at the back of the book, and in between there are several lessons, and these lessons help you to solve these problems. In this case, there is no specific lesson, but we will see them coming up in a few moments. So let's go straight to problem 676. It says, let A and B be real numbers for which you have this equation. a over b plus a plus 10b plus b plus 10a is equal to 2, right? So the question is find all possible values for a over b. Now you'll see that this is one equation, this is a single equation in two unknowns, right? So you can't solve for a and b because you've got more unknowns than equations. But what you can find the ratio of a to b, and that is the question that is asked. Find all possible values of a over b. Okay. So the way to do that is take this equation and flatten it out by multiplying right throughout by the common denominator being b into b plus 10a. And when you do that, you will get this part here. You can obtain by cross multiplication, a times that, ab plus 10a squared. And this way, you cross multiply, you get ab plus 10b squared. But you must be careful. What happens when you're cross multiplying is you're actually multiplying right throughout by b into b plus 10a, and you get this part. So on the right-hand side, you have to do the same thing. And when you multiply this by b into b plus 10a and simplify, you will get that expression. Now, if you bring all the a squareds and the ab's and the b squared together, you will get this equation, and eventually you come to this. So at this point here now, where do we proceed? This actually factorizes. Right? When you try to factorize it, you will see you get a minus b into 5a minus 4b equals 0. Right? You know how to factorize a trinomial, and this is what you get. And therefore, you will have that a is either equal to b, either this is 0, in which case a is equal to b, or this is 0, which means that a is equal to 4b divided by 5. When this is 0, then 5a is equal to 4b, and a will be equal to 4b divided by 5. But the question is to find a over b. So if you divide on both sides by b, you will get a over b. That's got two values. It's either equal to 1 or 4 over 5. And these are the two possible values of a over b. All right, there is an alternate method to solve the same problem, because the problem is to find a over b. So why don't we give a name to this single object and call this thing x? So this is why we said let x be equal to a over b, and then substitute for x here. This substitute for a over b at least. Here you can substitute straight away to get x. But this thing here, we don't have a over b in this. So we'll just repeat that. Now try to create an a over b here. The way to do that is to divide the numerator and denominator both by b. Now remember, when you got any fraction, 3 over 5, you can multiply 3 by anything you feel like. This is the same as 3 over 2. If you multiply both by half, or if you multiply both by 4, 4 times 3, 4 times 5. So you can multiply the numerator and denominator by the same quantity. So in this case here, I can multiply by 1 over b, numerator and denominator, and then you get a over b, and then, in other words, you're dividing by b. You divide this by b, you divide that by b also, you get 10. You do the same thing at the bottom, and you don't do anything to the side, because this fraction here is what we are replacing. We're not replacing the 2. All right. And now here you've got the x again. So if you replace a over b by x, because x is equal to a over b, then you have a single equation involving x. And when you simplify that, you will get this equation here, and this is a trinomial in just one variable, namely x. And then you can solve for x here, right? It's exactly the same as that. And when you solve for x, you'll get two values. X is 1 or 4 over 5, right? Which is x is a over b, you see? So you will get those two values. And you can factorize this. I'm not going to do that. The answer was already in the previous case, if you're alert enough. Okay, so let's get on to the next problem. So this is problem 196 in the book. So what is this problem saying? It says if x is equal to this quantity, determine this expression in terms of x. Now, you've got x is equal to 1 plus a quarter plus 1/9 plus 1/16 plus dot, dot, dot. It means that we're not stopping anywhere. We're going on, right? And there's a pattern here. If you look at this, this is really a half squared. This is 1/3 squared. And this is 1/4 squared. So what you are doing is you're adding the squares of 1, and then 1/2, 1/3, 1/4. Naturally, the next one will be 1/5 all squared, plus 1/6 squared. That's what I've got here, 1/5 squared, plus 1/6 squared, plus 1/7 squared, plus 1/8 squared. And I've written x out with more terms than what we see here, right? Now, there's a determine this object in terms of x, right? So what do you do here? You'll notice that I don't know what this is, but let's give a name to this. So we'll say let y be equal to this. 1 plus 1/9. That's 1/3 squared, 1/5 squared, 1/7 squared, 1/9 squared. So it's the sum of the squares of the odd terms, the terms with odd denominators. All right, so they say find this in terms of x. So if you go back to x here, you will see that you're adding the odd terms or the alternate terms in this expression, right? And those terms, 1 plus 1/9 plus 1/24, and so on, you've just given it a name. You call it y, right? But there are some other terms which are missing. Those are the first, third, fifth, and seventh terms. But if you look at the second term, the even terms, the fourth one, the sixth one, and this, that's missing. So this part here is equal to y plus these other terms. But if you look at those terms, you will see that the denominators are all multiples of 4. 4, 16, 36, 64, because you are squaring an even number, you see. So when you square an even number, the result is a multiple of 4, because you get 2 squared when you're squaring 2 times something. So it's a multiple of 4. Then we take out that multiple of 4. It's common right throughout the remaining parts. Take out the multiple of 4, and you have quarter. And what remains? Quarter goes into this 1 time. Quarter goes into 1/16, 1/4 times. And then 1/36, it's 1/9 times. And 1/64 is 1/16 times. So we're taking care of all the terms here. But this part here is exactly y. Right? There's it. Oh, I'm sorry. This is x. This is x. So you got 1/4 times x. Right? So on the left-hand side, you got x. On the right-hand side, you got y plus a quarter x. So to get rid of the quarter, you multiply right throughout by 4. Right? And the problem is to find that. That's y in terms of x. So you make y the subject. Right? And then you can work out y in terms of x. 4y equals 3x. So y is equal to 3x over 4, and that gives you the answer to this problem. Now, the only question here is you've got an infinite number of terms here which are being added, right? What is the meaning of that? There's no meaning to the sum of infinitely many terms. But when you do convergence of geometric series, this question arises because even in geometric series, sometimes you got the sum to infinity. Right? It means that the sum, there is a finite value to these, although you are adding infinitely many positive numbers, there's a finite value. And this particular series, they call this a series when you're adding, it converges. Right? In other words, it approximates a certain number. The larger you take the number of terms, you get closer and closer to a certain number. And so, in other words, we already know the sequence, the series converges because they have given a name to it. Sometimes the series doesn't converge, but in this case it does. Okay. It might interest you to know that this thing here, when you work out the sum to infinity of that, you'll get quite a remarkable answer. This thing converges to pi squared over 6. Curious, extremely curious that you've got all these positive integers or fractions and when you take more and more terms and add them, you get closer and closer to this number here. All right, so let's get on to the next problem. So the next problem is this one. How many zeros are there at the end of the number? You got a square of a terribly large number, and you got the square of another large number. And a calculator would not be able to write this down because there are too many figures in this. It'll only approximate. And even this too, there are too many figures in this. So how do you know how many zeros there are at the end of this number? When you calculate the square and subtract from the square of this, how do you know the number of zeros? Well, you can see that this is a difference of two squares, right? As you can see, there's a square here, there's a square here, it's a difference of two squares. And whenever you got a difference of two squares, you can factorize. So let's give a name to simplify the calculations. We're going to call this number here A. I've written it down, and I didn't bother about all the other stuff in between. I just wrote down the first few digits and the last 5 digits because the question is what happens at the end of that number. So let me see what happens at the end of this, and we call this B. Right? The same kind of a thing. We should have had a number of ... because there are some other digits there. And we need to calculate A squared minus B squared. So that is the question. And we know that A squared minus B squared is a difference of two squares, and it factorizes as A minus B into A plus B. So let us see what A minus B is. And we are only interested at the end. So when you subtract these two, you'll get 5 minus 5 is 0. 7 minus 2 is 5. So 5 minus 4 is 1. 5, and so on. So at the end, I'm interested in what happens at the end. That's A minus B. And A plus B, you'll add these numbers. 5 plus 5 is 10. 1 plus 7, 8 plus 1 plus 7 is 8. 8 plus 2 is 10. 1 and 5, 6 and 4, 10 again. 1 and 6 is 7, and 1 is 8. Right? And then there are lots of other things here. Okay. Well, actually, you have a 1 here and you have a 7 here as well. Okay. Um, I'm sorry, there's a 5 here, I think. Okay. So now we need to multiply these two numbers. But you will see when you multiply these two numbers, you'll have, this is 10 times something, right? The a minus b is 10 times something. That's something, I'm giving it a name. This is a number which ends in 1, 5. We're calling it x. And then you're going to multiply this by a plus b. And a plus b is 1,000 times something. Right? And that's something that ends in 78, and I'm calling that y. All right, so when you multiply these two things, you get 10 times 1,000, which is already 10,000, right? And times x times y. Right? Now, so we're left with multiplying these two numbers, x times y, but I'm interested to see what x, y ends in, right? Because I want to know how many zeros there are at the end. But when you multiply x, y, there's x, y is some number which goes up to 1, 5. And here it is some number which goes up to 7, 8. Oh, okay. I can't delete that. And when you multiply this out, you're interested only at what happens at the end, and this is what you see. Okay, so xy is it's 10 times something. So you've got 10,000, and xy is 10 multiplied by some number which finishes off with 1, 7. Right. So now you can see how many zeros there are at the end of the product. It's got 5 zeros because this thing here doesn't end in 0. See, you have to check to see whether this last number is 0. If it is 0, you continue. So in this case, you stop here, right? So how many zeros are there at the end? When you multiply these two things, you're going to have 4 zeros, another one more 0. So the answer is 5 zeros. Okay, so that without a calculator, you can actually calculate this thing by using the difference of two squares. Okay, let's get on to the next problem. Here, the question is, determine the sum of all integers x which satisfy the equation, this thing here. So you got some number raised to some number equals 1, but there's an x in it. If I put different values for x, if I put x equal to 5, for instance, then I will have a number here, and here I will have a power. If I put x equals 5, I got 2019 minus 5, which is 2014, raised to, and you put x equals 5 here, and then the exponent will be 2025, 2014 to the power of 2025. That's what this will become when x equals 5, and that is certainly not equal to 1. So the question is, for which values of x is this equal to 1? Okay, the answers are given here. For one thing, if the base number, if this is 1, it doesn't matter what the power is, this will be 1. So the first case is where this 2019 minus x is equal to 1, right? And then when you solve for x here, you'll get x is equal to 2018. Okay. And then the second case is where the numerator is 0. Any number raised to the power of 0 is equal to 1. Okay. So you want the numerator to be 0 and not numerator, the exponent. A to the power of 0 is always 1. So if the exponent is 0, then this will give you 1. So then you solve for that. 2020 plus x equals negative 2020, and that gives you the second value of x. So the first equation is that, and that gives you, oh, I'm sorry, the first equation was that, and that gives you a value for x. The second one was the exponent is equal to 0, and there you have a value for x. Right? And then the third case, there is a third case which might not be very easy to see. The third case is when this base is negative 1. You can have negative 1 to a power equal to plus 1. But as long as you got an even power, negative 1 to any even power is equal to 1. So I could have had that this base is negative 1, but the power will have to be an even number. So the base equal to negative 1, I've captured it here, and the power or the index or the exponent, that must be equal to an even number. Right? So you've got these two solutions. X is equal to this or that, and there is a third value for x. So let's look at this third value. When this is equal to x is negative 1, we can solve for x. X is equal to 2019 plus 1. So this is your third value. But we need to have that the base is negative 1 and the exponent is an even number. Right. So in this case, what is the exponent? The exponent is this. Now, if the value of x is 2020, then 2020 plus 2020 is certainly an even number. So that's okay. This is satisfied. Okay, but the actual value of x is 2020. So the three numbers which are being, there are three solutions, right? They're asking you to find the sum of all integers. So integers, because you are allowed negative 2020, which satisfy this equation. So there are three numbers, sum. When you add those three numbers, 2020 minus 2020 cancels off, and the answer is 2080. All right, so you just add these three integers and you'll get to the answer. All right, we'll go on to the next problem. And it says how many of the numbers, and you're counting all the numbers from 1 to 2014. The question is how many of these numbers are divisible by neither 11 nor 13? So that's the question. Okay, so you've got 2014 numbers, as you can see. So this question says how many of these numbers, all the numbers from 1 to 2014 are listed here. How many of these numbers are divisible by neither 11 nor 13? All right. So to analyze this question, we list all the numbers from 1 to 2014, and we ask ourselves whether each of them is divisible by 11 or if it's divisible by 13. Okay, obviously, none of these are divisible by 11 or 13. The first one that comes up, which is divisible by 11, is that one, right? And if you keep going on, the next one will be 22. So these numbers, 11, 22, 33, and so on, they are divisible by 11. And how many of them are there? Well, it's the same as asking the question 11, 22, 33, all the way. So how many 11s are there in 2014? That is really the question. And that's a division sum. Right? How many 11s are there in 2014? We asked this question here. So you have to divide 2014 by 11, and you see it's 183 remainder 1. Okay, you have to know how to divide this without using the calculator. So it means that you go up to 2014, and if you take 1 away from that, 2013, right? This number here is 11 times 183. So this is also a number which is, and that's equal to 11 times 183, right? And then you add 1 to that, you get to this. So the number of 11s is 11, 22, and so on, going all the way up to 183. And the answer to this question is 183. So 183 11s in 2013. All right, but the question also says it must be divisible by neither 11 nor 13. So let us look at all the multiples of 13. So you have 13, and you have 26. 13 times 2 is 26. And now the same question, how many 13s are there in 2014? And you do the same thing here, and you'll see you get 154, remainder 12. So when you take away 12 from this, and that's where you get 2002, right? You take away 12 from that. This thing here is a multiple of 13, right? Because it's 13 times what? It's 13 times 154. So this is 13 times 154. And then when you add 12 to that, you get to that. So the number of 13s is 154. So the answer is 154. Because the next one will be 2015, you see. Because you have to add 13 to 2002 to get, so therefore you got, it's exactly 154. So your feeling would be that the total number of, numbers which are divisible by either 11 or 13, right? The question is, how many of them are divisible by neither 11 nor 13? So you have to really look at all the crosses. 12 is one of those crosses, and all in between. So you want to know how many numbers are there which have got crosses in it. Well, to do that, you have to ask yourself how many numbers are actually circled. All right. So it looks as if you've got 183 plus 154. So all the reds and all the blues, and the 183 reds, 154 blues. Okay, but there's a problem, because you see, amongst the numbers which you see, which is a multiple of 13, is this. This is 13 times 11, and this is 13 times 22. This is 13 times. So you would have ringed all these, because this is yeah. So this is 13 times 154. Right? But this is also a multiple of 11, you see, because this is 13 times 11. So So I would have ringed this thing when I was ringing 11s, I would have ringed this thing. So in other words, these numbers would have been ringed twice. So when you are counting 183 plus 154, you're not getting a proper count because some of these things are ringed twice. So you have to remove the number of numbers which are ringed twice because you only want to count them once, right? All right. So what are those numbers? They are, firstly, 13 times 11 is the very first one. And then after that is all the multiples. 13 times 11 is 143. And all the multiples of 143, right, which are less than 202. So the question is how many 143s are there in this? Again, now you take long division. And you see that the 14 and the remainder is 12. So this last number here is 14 times 143. Remainder is 12. So when I take away 12 from that, I get 2002. That's the one we're looking at. That's 14 times this. So the number of things which are counted twice is, this is 143 times 1. One times that, 2 times that, 3 times that, 14 times that. So there are 14 numbers which are repeated. And you have to subtract 14 from this because you would have counted these twice. You need to only count them once, right? So this gives you the total number of numbers, 337, 323. The total number of numbers which are divisible by either 11 or 13, right? But your question is, which are divisible by neither 11 nor 13? So you have to look at all the crosses. And to do that, the total number of numbers is 2014, as you can see. And you have to remove all those which have been ringed. So the total number of things which have been ringed is 323, which we just saw. So those are the numbers which have got crosses next to them. And when you work that out, you get something. All right. So that's how you do this. It's an interesting problem to look at, to understand what you mean by division. Division really says, how many 11s are there in 2014? That's the question that he's asking. And how many are left over? Because this is not really a multiple of 11, but there is a multiple of 11, which is slightly before that, right? And how many are left over? Okay, so that takes us to the next question.